tonight, we're going to talk about something that might make you uncomfortable. Something that challenges everything you think you understand about reality. Because here's the truth. Almost everything in the universe is invisible. Not metaphorically invisible. Not hidden somewhere we can't reach. Actually, genuinely invisible matter that doesn't interact with light at all. That passes through ordinary matter like a ghost, that we cannot see or touch or detect directly. And here's the part that should really bother you. This invisible stuff makes up about 85% of all the matter in the universe. Everything you can see, every star, every planet, every galaxy, every atom in your body is just a minority, the leftover, the 15%. The universe is held together, shaped, and dominated by something we cannot see and do not understand. By the end of this journey, you're going to grasp something profound and unsettling. The universe you think you know is just the tip of the iceberg, and the iceberg itself is made of something we've never touched. Before we begin, if you find these explorations of cosmic mysteries fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's dive into the invisible universe. The problem that wouldn't go away. Let me start with a mystery that's been bothering scientists for nearly a century. A problem so fundamental that it threatens to overturn our understanding of how the universe works. In the 1930s, an astronomer named Fritz Zwicky was studying galaxy clusters, enormous collections of hundreds or thousands of galaxies bound together by gravity. He focused on the Coma cluster, about 300 million light-years away, containing over 1,000 galaxies. Zwicky did something clever. He measured how fast galaxies in the cluster were moving. Galaxies in clusters orbit around the cluster's center of mass, pulled by the combined gravity of all the galaxies. By measuring their speeds, Zwicky could calculate how much mass must be present to hold the cluster together. Then he did something else. He added up all the visible matter, all the stars and all the galaxies. He calculated how much mass all that starlight represented. The numbers didn't match. Not even close. The galaxies were moving far too fast. Based on the visible matter, they should have been flying apart. The cluster shouldn't exist. The gravity from visible matter simply wasn't strong enough to hold everything together. Zwicky calculated that the cluster needed about 400 times more mass than he could see. There had to be some kind of invisible matter. He called it dunkle matter. Dark matter in German, providing the extra gravity. Most scientists ignored him. The idea seemed absurd. How could most of the universe's matter be invisible? Surely, there was a simpler explanation. Maybe Zwicky's measurements were wrong. Maybe there was some error in his calculations. Maybe he'd missed something obvious, but Zwicky hadn't missed anything. And the problem wouldn't go away. Galaxies that spin to fast forward to the 1970s. Astronomer Vera Rubin was studying how galaxies rotate. She focused on spiral galaxies like our own Milky Way, disc-shaped collections of stars, orbiting around a central bulge. Here's what should happen. Stars closer to the center should orbit faster than stars farther out. This is basic orbital mechanics, the same reason Mercury orbits the Sun faster than Earth does, and Earth orbits faster than Mars. In a spiral galaxy, most of the visible mass is concentrated toward the center. As you move outward, the density of stars decreases. Based on the visible matter, stars on the outer edges should be moving relatively slowly. Rubin measured the orbital speeds of stars at various distances from galactic centers. She used spectroscopy, analyzing the light from stars to determine their velocities. Based on the Doppler shift, the same effect that makes ambulance sirens change pitch as they pass you. What she found didn't make sense. Stars on the outer edges of galaxies were moving just as fast as stars closer to the center. Some were even moving faster. The rotation curves graphs showing orbital speed versus distance from center were flat instead of declining. This was impossible. Or rather, it was impossible unless there was additional mass beyond what we could see. Mass that extended far beyond the visible disk of stars. Mass that was distributed in a large spherical halo surrounding the entire galaxy. Rubin calculated how much invisible matter would be needed to explain the rotation curves. The answer was shocking. Roughly 5 to 6 times more matter than all the visible stars combined. Every galaxy she studied showed the same pattern. Flat rotation curves. Too much gravity. Missing mass. The evidence was becoming undeniable. There was something out there, something invisible, something providing gravity, something far more abundant than ordinary matter. Dark matter wasn't just Zwicky's wild idea anymore. It was a genuine mystery demanding explanation. What dark matter is before we talk about what dark matter might be. Let's eliminate what it definitely isn't, because scientists spent decades trying to explain away dark matter as something ordinary, something we just hadn't noticed. Our first possibility, maybe it's just gas. Clouds of hydrogen and helium floating between stars, not glowing bright enough to see easily. Problem: we can detect gas through other means. Hot gas emits X-rays. Cold gas absorbs specific wavelengths of light from background stars. We've searched extensively. The gas is there, but nowhere near enough to account for dark matter. Not even close. Second possibility, maybe it's dust. Tiny particles of rock and ice scattered through space. Too small to see individually, but collectively massive. Problem: dust blocks and scatters light. It creates shadows and reddens starlight. We see these effects in some regions, but not nearly enough to account for the missing mass. Dust is there, but it's a tiny fraction of what we need. Third possibility, maybe it's dead stars. White dwarfs, neutron stars, black hole stellar remnants that no longer shine brightly, but still have mass. Problem: we can detect these objects through various means. Neutron stars emit radiation. Black holes reveal themselves through their gravitational effects on nearby stars and gas. We've counted them. They don't add up to nearly enough mass. Fourth possibility, maybe it's planets. Lots and lots of planets floating between stars, ejected from their original systems. Too far from any star to reflect much light. Problem: planets form from the same material as stars' ordinary matter made of atoms. And we have strict constraints on how much ordinary matter exists in the universe. From observations of the cosmic microwave background, and from measurements of primordial element abundances, the numbers don't work. There can't be enough planets. Fifth possibility, maybe it's Macho's massive compact halo objects. This was a serious proposal in the 1990s. Maybe galactic halos were filled with planet-sized or brown, dwarf-sized objects, things too small to be stars, but massive enough to provide gravity. This hypothesis was testable. MACHOs might be invisible, but they still have gravity. If one passed between us and a background star, its gravity would lens the starlight, briefly brightening the star. This is called gravitational microlensing. Scientists monitored millions of stars for years, looking for these brief brightening events. They found some, but far too few. MACHOs exist, but they account for maybe 1 to 2% of the needed mass, not 85%. One by one, every conventional explanation failed. Dark matter wasn't gas or dust or dead stars or planets or dim objects we'd overlooked. It was something fundamentally different. Something that doesn't interact with light at all. Something that passes through ordinary matter like it isn't there. Something we've never seen in laboratories. Something completely unknown. What we know about dark matter. So if we can't see dark matter, how do we know anything about it? How can we study something invisible? Through gravity. Only through gravity. Dark matter doesn't emit light. It doesn't absorb light. It doesn't scatter light. It doesn't interact with electromagnetic radiation in any way we can detect. But it has mass. And mass creates gravity. And gravity we can observe. Here's what we know. Dark matter interacts gravitationally. It pulls on ordinary matter with gravity. It holds galaxy clusters together. It causes galaxies to rotate faster than visible matter alone would allow. It bends light through gravitational lensing. Everywhere we see its gravitational signature. Dark matter is distributed in large halos around galaxies. The rotation curves tell us this. The flat speeds at large distances mean dark matter extends far beyond the visible disk of stars. In a roughly spherical distribution, our Milky Way sits inside a dark matter halo, extending perhaps 600,000 light-years from the galactic center, far larger than the visible galaxy. Dark matter is cold. This is jargon, but important. Cold means the dark matter particles are moving slowly compared to the speed of light. This matters because if dark matter were hot, moving near light speed, it couldn't clump together gravitationally to form the structures we observe. It would be too energetic to spread out. The fact that dark matter halos exist around individual galaxies tells us the particles must be cold, moving slow enough to be captured by galaxies' gravity. Dark matter doesn't interact with itself very much. If dark matter particles collided with each other frequently, they lose energy and collapse toward galactic centers, forming dense cores. We don't see this. Dark matter halos are relatively diffuse. This tells us dark matter particles rarely collide, even with each other. They pass through each other just as they pass through ordinary matter. Dark matter is abundant. Roughly 85% of all matter in the universe is dark matter. Only about 15% is ordinary matter, the protons, neutrons, and electrons that make up atoms, stars, planets, and people. Dark matter is ancient. It's been around since the very early universe. We can see its gravitational effects in the cosmic microwave background, the afterglow of the Big Bang. From when the universe was only 380,000 years old, dark matter was already there, already clumping, already shaping the formation of structure. These are the facts. This is what observations tell us. And every single observation, from galaxy rotation curves to gravitational lensing to the cosmic microwave background to computer simulations of structure formation, points to the same conclusion. Dark matter exists. It's real. It's everywhere. And we have no idea what it is. Gravitational lensing. Seeing the invisible. Of the most beautiful ways we detect dark matter is through gravitational lensing. Let me explain how this works, because it's both elegant and definitive. Einstein's general relativity tells us that mass curves spacetime. Light traveling through curved spacetime follows a curved path. So when light from a distant galaxy passes near a massive object like a galaxy cluster, the path of the light bends. This bending acts like a lens. The massive object in the middle magnifies and distorts the light from galaxies behind it. Sometimes we see multiple images of the same background galaxy. Sometimes the background galaxy gets stretched into an arc or ring. The amount of lensing depends on the total mass of the lensing object. All the mass, visible and invisible. Scientists have used gravitational lensing to map the distribution of mass in galaxy clusters. The technique is remarkably precise. By studying how background galaxies are distorted, you can create a map showing where mass is concentrated, regardless of whether that mass glows. The results are striking. The maps show far more mass than can be accounted for by visible matter, and the distribution of mass doesn't always match the distribution of stars and gas. The most famous example is the Bullet Cluster, the galaxy clusters that collided about 150 million years ago. When scientists mapped the mass distribution using gravitational lensing, they found something remarkable. The hot gas from the two clusters visible in X-rays had collided and slowed down, piling up in the middle. But most of the mass, revealed by gravitational lensing, had passed straight through to large clumps of mass, one on each side of the collision, with the gas between them. This is exactly what you'd expect if most of the mass is dark matter. Dark matter doesn't collide with itself or ordinary matter. When the clusters collided, the dark matter halos passed through each other like ghosts, while the gas collided and stopped. The Bullet Cluster is sometimes called direct proof of dark matter. It's hard to explain any other way. The mass is there, gravitational lensing proves it. But it's not where the gas is. It's somewhere else, invisible, having passed through the collision unimpeded. Gravitational lensing has now been used to map dark matter in thousands of galaxies and galaxy clusters. Every single observation confirms the same picture. There's far more matter than we can see. It's distributed in large halos, and it behaves exactly like dark matter should behave. The cosmic microwave background, ancient evidenticism, of the most compelling evidence for dark matter comes from the very early universe, from light that has been traveling toward us for over 13 billion years. The cosmic microwave background, or CMB, is the afterglow of the Big Bang, when the universe was about 380,000 years old. It cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this moment, the universe was opaque and hot plasma, where photons constantly scattered off free electrons. When atoms formed, photons can suddenly travel freely. The universe became transparent. Those photons have been traveling through space ever since, and we detect them today as microwave radiation coming from all directions. The CMB is remarkably uniform. Its temperature is about 0.7 to 5 Kelvin everywhere you look. But there are tiny variations, about 1 part in 100,000. Some regions are slightly warmer, some slightly cooler. These tiny temperature variations are incredibly important. They represent density variations in the early universe, regions that were slightly more dense than average, regions that were slightly less dense. These density variations eventually grew through gravity into all the structure we see today. The denser regions attracted more matter, becoming even denser. eventually collapsing into galaxies and galaxy clusters. But here's the crucial point. The pattern of variations in the CMB depends on what kinds of matter existed in the early universe. Ordinary matter atoms, protons, neutrons interact with photons. Before atoms formed, ordinary matter was tightly coupled to radiation through electromagnetic forces. This interaction created pressure that resisted gravitational collapse. Ordinary matter and radiation acted like a fluid, sloshing back and forth, creating acoustic oscillations, sound waves in the primordial plasma. Dark matter is different. Dark matter doesn't interact with photons or with itself. It only feels gravity. So dark matter wasn't coupled to the radiation. It could collapse gravitationally without resistance. This difference left distinctive imprints in the CMB. The pattern of temperature variations, which peaks are strongest, where they appear in codes. Information about how much ordinary matter and how much dark matter existed in the early universe. Scientists have measured the CMB with extraordinary precision using satellites like WMAP and Planck. The data is exquisite, and it tells us unambiguously the universe contains about 5 times more dark matter than ordinary matter. The ratio is roughly 85% dark matter, 15% ordinary matter. This isn't an estimate based on galaxy rotation curves or some indirect inference. This is a direct measurement from the structure of the early universe, from light that has been traveling for over 13 billion years, carrying information about what the universe was like when it was young. The early universe contained dark matter, lots of it, 5 times more than ordinary matter, and if it was there in the beginning, it's still here now. Dark matter doesn't decay or disappear. It's still around, still invisible, still holding the universe together. # computer simulations. Building universes * one of the most powerful ways scientists test theories is through computer simulations. If we understand how gravity works, we should be able to simulate the evolution of the universe and see if we get something that looks like reality. Cosmologists have run enormous simulations of structure formation, how the universe evolved, from the nearly smooth state we see in the CMB to the lumpy state we see today, with galaxies clustered along filaments surrounding vast voids. They start with initial conditions matching the CMB observations, tiny density variations. Then they let gravity do its work, calculating how matter clumps over billions of years. The simulations only work if you include dark matter. If you try to run them with ordinary matter alone, you don't get galaxies and galaxy clusters when you should. Structure forms too slowly. The universe today would still be nearly smooth, nothing like what we actually observe. But when you include dark matter, 5 times more dark matter than ordinary matter, not interacting with light or with itself, only feeling gravity, the simulations work beautifully. You get galaxies forming at the right times. You get galaxy clusters. You get the cosmic web, the filamentary structure of matter on the largest scales. You get rotation curves matching observations. You get gravitational lensing effects matching observations. The simulations reproduce reality in stunning detail. Not perfectly, there are still puzzles and discrepancies we're working to understand, but the overall agreement is remarkable. This is powerful evidence. It's one thing to say we need dark matter to explain galaxy rotation curves. It's another thing entirely to simulate the entire evolution of the universe over 13.8 billion years and have it match reality, but only if you include dark matter. The simulations tell us dark matter isn't just an ad hoc fix for a few observations. It's a fundamental component of the cosmos, essential for understanding how the universe evolved from its smooth beginning to its structured present. What could dark matter be? So dark matter exists. The evidence is overwhelming. But what is it? What kind of particle or object could explain all these observations? This is where things get speculative, because despite decades of searching, we haven't detected dark matter particles directly. We know they're there through gravitational effects, but we haven't caught one yet. Here are the leading candidates. WIMP's weakly interacting massive particles. This has been the favorite hypothesis for decades. The idea is that dark matter consists of particles with mass somewhere between 10 and 1,000 times the mass of a proton, interacting through gravity and the weak nuclear force, but not electromagnetism. WIMPs are attractive theoretically. Many theories beyond the standard model of particle physics predict particles with exactly these properties. The supersymmetry theory, for example, predicts a neutralino that could be the dark matter particle. Asterisk WIMPs would be everywhere. Earth is moving through the Milky Way's dark matter halo at about 220 kilometers per second. That means billions of WIMPs are passing through your body every second. They pass right through, without interacting because they don't feel electromagnetic forces. But very occasionally, a WIMP might collide with an atomic nucleus through the weak force. Asterisk scientists have built extremely sensitive detectors trying to catch these rare collisions. Detectors deep underground to shield from cosmic rays. Detectors cooled to near absolute zero to minimize thermal noise. Detectors containing hundreds of kilograms of ultra-pure materials. Asterisk so far, nothing. No definitive WIMP detection. The constraints are becoming tight. If WIMPs exist, they're either less massive or interact even more weakly than originally thought. Asterisk axions, asterisk. These are hypothetical particles originally proposed to solve a different problem. In particle physics, the strong CP problem. Axions would be extremely light, perhaps a trillionth the mass of an electron, but incredibly abundant. Asterisk unlike WIMPs, individual axions wouldn't be detectable, but collectively, in sufficient numbers, they behave as dark matter. Axions might interact very weakly with photons light under certain conditions, particularly in strong magnetic fields. Asterisk experiments are searching for axions by looking for these subtle light-axion interactions. So far, no confirmed detection, but the search continues. Asterisk sterile neutrinos. Asterisk neutrinos are real particles we've detected elusive, nearly massless particles that interact only through the weak force and gravity. Ordinary neutrinos come in 3 types or flavors. Asterisk, but theories predict there might be additional neutrinos that don't interact through the weak force at all, only through gravity. These sterile neutrinos would be essentially invisible, detectable only through gravity. Asterisk if sterile neutrinos exist and have the right properties, they could be dark matter. Several experiments are searching for hints of their existence, particularly looking for subtle signals in X-ray emissions from galaxy clusters. Asterisk primordial black holes. Asterisk what if dark matter isn't particles at all, but black holes formed in the very early universe, before the first stars? Asterisk if conditions were right in the first fraction of a second after the Big Bang, regions of space might have been dense enough to collapse directly into black holes. These primordial black holes would be dark matter. They have mass, they interact gravitationally, but they don't emit light. Asterisk the idea is intriguing but faces challenges. Primordial black holes would occasionally pass through star systems, causing detectable perturbations. We can constrain their abundance through various observations. Current data suggests primordial black holes can't account for all dark matter, though they might be a component. Asterisk something else entirely. Asterisk perhaps dark matter is none of these. Perhaps it's a type of particle or phenomenon we haven't imagined yet. Something not predicted by current theories, something completely unexpected. Asterisk this isn't just speculation. History teaches humility. When scientists first detected radio emissions from space, they didn't expect pulsars rapidly spinning neutron stars. When they first observed gravitational lensing, they didn't expect it to reveal dark matter halos. Nature surprises us. Asterisk dark matter might be something so unexpected, so unlike anything in the standard model, that we won't recognize it until we detect it. Asterisk the search continues. In laboratories, in space-based observatories, and deep underground detectors, scientists are looking for any hint, any clue, any signal that might tell us what dark matter actually is. Asterisk hash. The dark matter halo you're moving through. Asterisk here's something most people don't think about. You're inside a dark matter halo right now. Asterisk the Milky Way sits inside a roughly spherical halo of dark matter extending perhaps 600,000 light-years from the galactic center, about 6 times the diameter of the visible galaxy. Asterisk the total mass of this halo is estimated at about 1 to 2 trillion times the mass of the Sun. For comparison, the Milky Way's visible matter, all to 100 to 400 billion stars plus gas and dust, is only about 100 to 200 billion solar masses. Asterisk so the dark matter halo outweighs all the visible matter by a factor of 5 to 10. The Milky Way, like all galaxies, is dominated by dark matter. The stars and gas we see are just passengers, trapped in the gravitational well of the dark matter halo. Asterisk Earth is located about 26,000 light-years from the galactic center, deep inside this halo. The local dark matter density here is estimated at about 0.3 GeV per cubic centimeter. That might not mean much to you, so let me convert it. Asterisk, that's roughly equivalent to about 6 proton masses per cubic centimeter, or about 10 to 24 grams per cubic centimeter. Asterisk, that sounds incredibly low, and it is dark matter is diffuse. But remember, dark matter particles are everywhere. Your body occupies about 70,000 cubic centimeters, about 70 liters. At any given moment, your body's volume contains dark matter equivalent to about 420 proton masses. Asterisk, but these aren't protons. They're dark matter particles, probably much more massive. If dark matter consists of WIMPs with mass about 100 times a proton's mass, then your body's volume contains about 4,000 to 100 dark matter particles at any moment. Asterisk. And Earth is moving through the halo at about 220 kilometers per second, roughly 490,000 miles per hour. That's our orbital speed around the galactic center. Asterisk, this means billions of dark matter particles pass through you every second. They pass through Earth, through the moon, through the sun. They pass through everything without interacting. Asterisk, you are constantly bathed in a stream of invisible particles. They've been flowing through you your entire life. They'll continue flowing through you until you die, and you feel nothing. You can't detect them. They pass through like you aren't there. Asterisk, that's dark matter. Invisible, intangible, everywhere. # dark matter in the larger universe. Asterisk, let's zoom out beyond the Milky Way and look at dark matter on cosmic scales. Asterisk, galaxy clusters, collections of hundreds or thousands of galaxies bound by gravity are the largest gravitationally bound structures in the universe. Each cluster sits inside an enormous dark matter halo. Asterisk, the Coma cluster, which Fritz Zwicky studied in the 1930s, has a dark matter halo extending about 10 million light years across. The total mass is roughly 10 quadrillion solar masses. About 85% of that is dark matter. Asterisk, on even larger scales, galaxies and galaxy clusters aren't distributed randomly. They're organized into a cosmic web, filaments of matter surrounding vast voids. Asterisk, this structure formed through gravitational collapse over billions of years. Denser regions attracted more matter, becoming denser still. Less dense regions lost matter to their surroundings, becoming voids. Asterisk, dark matter drove this process. Because dark matter doesn't interact with radiation, it could collapse earlier than ordinary matter. Dark matter formed the scaffolding, the gravitational framework that ordinary matter later fell into. Asterisk, imagine building a house. You first construct the frame, wooden or steel beams forming the structure. Then you add walls, insulation, siding. Dark matter is the frame. Ordinary matter, stars, gas, galaxies is everything else. Filling in the structure dark matter created. Asterisk, computer simulations show this beautifully. In simulations, dark matter collapses first, forming halos. Then ordinary matter falls into these halos, cools, forms stars and galaxies. The end result matches the universe we observe. Asterisk, without dark matter, the cosmic web wouldn't exist. Galaxies would be rare and isolated. Galaxy clusters wouldn't have formed. The universe would look completely different. Asterisk, dark matter isn't just a component of the universe. It's the dominant component. It shapes structure. It determines where galaxies form. It governs the evolution of cosmic structure over billions of years. Asterisk, when you look at a map of the universe showing the positions of millions of galaxies, arranged in filaments and walls surrounding voids, you're looking at dark matter's handiwork. The pattern you see is fundamentally a dark matter pattern, with ordinary matter tracing the dark matter distribution. Asterisk, # the mysteries that remain. Asterisk, despite all we've learned, profound mysteries remain. Questions we can't yet answer. Puzzles that keep cosmologists awake at night. Asterisk, the core cusp problem. Asterisk, simulations of dark matter halos predict they should have dense central regions, cusps, where density increases steeply toward the center. But observations of some dwarf galaxies suggest their dark matter halos have constant density cores instead of cusps. This discrepancy isn't fully understood. Is it a problem with our dark matter models, or with our understanding of how stars and gas affect dark matter distribution? Asterisk, the missing satellites problem. Asterisk, simulations predict large galaxies like the Milky Way should have hundreds of small satellite galaxies orbiting them, dwarf galaxies trapped in the larger galaxy's gravity. But we see far fewer satellites than predicted. The Milky Way has about 60 known satellites. Simulations predict hundreds or thousands. Where are they? Are they there, but too faint to detect? Or is something wrong with our simulations? Asterisk, 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 the too big to fail problem. Asterisk, asterisk, related to the missing satellites problem. Simulations predict the largest satellite galaxies should be more massive than observed. Some predicted satellites are too big to fail, too massive not to have formed stars, and be easily visible. Yet we don't see them. Why not? Asterisk, 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 Bryonic-Tully-Fisher relation. Asterisk, asterisk, this is an empirical relationship between a galaxy's total mass and ordinary matter baryons, and its rotation speed. The relationship is remarkably tight, suggesting a deep connection between ordinary matter and galaxy dynamics. But if galaxies are dominated by dark matter, why does this relationship exist? Why would ordinary matter, which is only 15% of the total, determine rotation speeds? Asterisk, 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 direct detection. Asterisk, asterisk, the biggest mystery, we still haven't directly detected a dark matter particle. Decades of experiments, increasingly sensitive detectors, and nothing. Is dark matter something we can detect in laboratories? Or does it interact so weakly that direct detection is impossible? Asterisk, these mysteries remind us how much we don't know. Dark matter exists, that's clear from observations, but the details remain murky. The particle identity remains unknown. The small-scale behavior remains uncertain. Asterisk, science is a process. We've made enormous progress understanding dark matter over the past 90 years. But we're not done. Every answer raises new questions. Every solved mystery reveals new puzzles. Asterisk, that's how science works. That's what makes it exciting. Asterisk, hash, hash, what if we're wrong? Asterisk, I need to address something important. What if dark matter doesn't exist? What if there's a simpler explanation we missed? Asterisk, some physicists have proposed alternatives. The most famous is modified Newtonian dynamics, or MOND, proposed by Mordechai Milgram in 1983. Asterisk, MOND suggests that maybe Newton's laws of gravity need modification at low accelerations. The regime that applies to stars in galactic outskirts. Maybe gravity behaves differently in these conditions, becoming stronger than Newton predicted. Asterisk, if true, this could explain galaxy rotation curves without dark matter. Stars on galaxy edges wouldn't need extra mass to explain their speeds. They'd just be feeling stronger gravity than we expect. Asterisk, MOND works remarkably well for explaining galaxy rotation curves. That's its strength. For individual galaxies, it matches observations as well as dark matter does, sometimes better. Asterisk, but MOND struggles with other observations. It has trouble explaining galaxy clusters. It struggles with gravitational lensing observations. It can't explain the cosmic microwave background patterns without adding something like dark matter back in. Asterisk, the bullet cluster is particularly problematic for MOND. The separation between where mass is revealed by lensing and where gas is revealed by X-rays is hard to explain if you're modifying gravity rather than adding dark matter. Asterisk, in MOND doesn't fit naturally into our broader understanding of physics. It's more of an empirical fix than a fundamental theory. There's no deeper theoretical framework explaining why gravity should change behavior at low accelerations. Asterisk, most physicists think dark matter is the better explanation. It fits more observations. It integrates naturally into cosmology and structure formation. It's predicted by several theories beyond the standard model. Asterisk, but the lack of direct detection is troubling. If dark matter particles exist, why haven't we found them yet? Are they harder to detect than we thought? Or are we looking in the wrong places? Asterisk, science requires humility. We could be wrong. Maybe dark matter isn't particles. Maybe it's something else, a modification of gravity we haven't imagined. Some new phenomenon in physics. Something unexpected. Asterisk, but right now, with the evidence we have, dark matter remains the best explanation. It's not perfect. There are puzzles and mysteries, but it fits the observations better than any alternative. Asterisk, that could change. Science is always provisional. New evidence could overturn current thinking. That's not a weakness, it's a strength. Science changes when evidence demands it. Asterisk, for now, dark matter stands as our best answer to the mystery of why galaxies rotate too fast, why clusters stay together, why the universe looks the way it does. Asterisk, hash, hash, living in a dark universe. Asterisk, let me bring this home. Let me explain what it means for you, personally, that most of the universe is invisible. Asterisk, you're sitting somewhere reading or watching this. You can see your surroundings, walls, furniture, maybe windows with views outside. The light entering your eyes comes from objects made of ordinary matter atoms, molecules, stuff that interacts with light. Asterisk everything you've ever seen. Everything anyone has ever seen is made of ordinary matter. That's the 15%, the minority component. Asterisk the remaining 85%. The dark matter is invisible. Always has been. Always will be. It doesn't emit light. It doesn't block light. It's transparent to light. You could never see it, no matter how good your eyes were. Asterisk, but it's there. All around you, passing through you constantly. Billions of dark matter particles flowing through your body every second. Through your brain, your heart, your bones. They don't interact with your atoms. They don't trigger any biological processes. They cause no harm. They just pass through like you aren't there. Asterisk the room you're in sits inside the Milky Way's dark matter halo. That halo outweighs all visible matter by a factor of 5 to 10. The dark matter dominates gravitationally. It holds the galaxy together. Without it, the Milky Way would fly apart. Asterisk Earth orbits the Sun, which orbits the galactic center. All of us moving through a sea of dark matter. We're like fish swimming in an ocean, completely unaware of the water. The dark matter is the medium we move through, invisible and intangible. Asterisk and beyond the Milky Way. Every galaxy sits in a dark matter halo. Every galaxy cluster sits in an even larger halo. The cosmic web, the largest structures in the universe, are fundamentally dark matter structures, with galaxies merely tracing the dark matter distribution like lights on a Christmas tree. Asterisk most of the universe is invisible to us. We see the lights, the stars, galaxies, glowing gas. But the scaffolding holding it all together, the framework shaping cosmic structure, the majority of matter all invisible. Asterisk that should be humbling. We live in a universe we cannot fully see. A universe where most of what exists is beyond our direct perception. A universe where the dominant component is something we don't understand. Asterisk, and yet we detected it. We've mapped it. We understand its gravitational effects. We can simulate its behavior. We know where it is, how much there is, how it's distributed. Asterisk that's remarkable. That's the power of science. We can't see dark matter directly, but we can infer its existence and properties through careful observation and logical reasoning. Asterisk we're limited beings. We can only see a narrow slice of the electromagnetic spectrum. We can only hear certain frequencies. We can only touch matter that pushes back against us electromagnetically. Asterisk, but we're also clever. We build instruments that extend our senses. We develop theories that predict what we can't see. We use indirect evidence to map the invisible. Asterisk dark matter is invisible. Yes, but it's not unknowable. We've learned an enormous amount about it, and we're learning more every day. Asterisk hash the search continues. Asterisk right now, as you're reading this, experiments around the world are searching for dark matter particles. Asterisk deep underground in mines and tunnels, shielded from cosmic rays by miles of rock, set ultra-sensitive detectors. Tanks of liquid xenon, cooled to -100°C, instrumented with thousands of sensors. If a dark matter particle collides with a xenon nucleus, the detector might catch it. Asterisk these experiments run for years, collecting data, searching for the incredibly rare signal of a dark matter interaction. So far, no confirmed detection, but the experiments keep running, getting more sensitive, ruling out more of the possible parameter space. Asterisk at CERN and other particle accelerators. Physicists are smashing particles together at enormous energies, trying to create dark matter particles in the lab. If dark matter particles exist and have certain properties, high-energy collisions might produce them, and we might see the telltale signs: missing energy carried away by invisible particles that escape the detectors. Asterisk these experiments haven't found dark matter yet either, but they've ruled out certain possibilities, narrowed the search, constrained what dark matter can and cannot be. Asterisk in space, telescopes are watching for indirect signals. If dark matter particles occasionally collide and annihilate each other, they might produce gamma rays or other radiation. Satellites like Fermi are scanning the sky, looking for unexpected sources of gamma rays that might be dark matter annihilation. Asterisk some scientists are looking at the Sun and Earth themselves. If dark matter particles interact weakly with ordinary matter, some should occasionally scatter off atoms in the Sun or Earth and lose energy, becoming gravitationally trapped. Over billions of years, dark matter would accumulate in the cores of these bodies. If these trapped particles annihilate, they might produce neutrinos, ghostly particles we can detect. Neutrino telescopes are watching for this signal. Other experiments search for axions using powerful magnets. If axions exist and interact with photons in magnetic fields, a strong enough magnet might convert axions into detectable photons. Several experiments are running, each exploring different possible axion masses. The search is comprehensive. Multiple approaches, multiple technologies, multiple experiments. Scientists are looking everywhere, trying everything they can think of. Because if we could detect a dark matter particle, if we could catch one, study it, measure its properties, it would revolutionize physics. It would tell us what exists beyond the standard model. It would reveal an entirely new sector of reality we've never accessed before. The stakes are enormous. The prize is understanding what 85% of the universe's matter actually is. Dark energy. An even bigger mystery. I need to mention something that might blow your mind even further. Dark matter isn't even the biggest mystery. So far I've been talking about matter stuff with mass. Stuff that clumps gravitationally, stuff that forms structures like galaxies and galaxy clusters. Dark matter is the dominant form of matter, but matter itself, ordinary plus dark, combined makes up only about 31% of the universe's total energy. Content. The remaining 69% is something even stranger. Dark energy. Dark energy is a mysterious force causing the universe's expansion to accelerate. In 1998, astronomers discovered that distant supernovae were farther away than expected, which meant the universe's expansion was speeding up rather than slowing down. As gravity would predict, something is pushing the universe apart, counteracting gravity, causing space itself to expand faster and faster. We call this something dark energy, though we have no idea what it is. Dark energy might be a property of space itself, a cosmological constant. Energy inherent in empty space, or it might be a dynamic field filling the universe. We don't know. What we know is that it's there. It's powerful, and it dominates the universe's energy budget. So let me give you the full accounting of what the universe contains. Ordinary matter, approximately 5%. This is everything made of atoms, stars, planets, gas, dust, you, me, everything we can see or touch. The stuff we think of as the universe. Dark matter, approximately 27%. Invisible matter that only interacts gravitationally, 5 times more abundant than ordinary matter. Forms halos around galaxies and shapes cosmic structure. Dark energy, approximately 68%. Mysterious energy causing the universe's expansion to accelerate. The dominant component of the universe, about which we understand almost nothing. Added up, 95% of the universe's energy content is dark, either dark matter or dark energy. Only 5% is ordinary matter. Everything you've ever seen, everything anyone has ever seen, everything in all of astronomy and astrophysics. Until the late 20th century, all of it is just 5% of what exists. We live in a universe where we don't understand 95% of the content. We can measure it, we can observe its effects, we can constrain its properties, but we don't fundamentally understand what it is. That should be both humbling and exciting. Humbling because it shows how much we don't know. Exciting because it shows how much there is still to discover. What dark matter tells us about reality. Let me step back and think about what dark matter means philosophically. What it tells us about the nature of reality. First, it tells us that reality extends far beyond human perception. We evolved to sense certain things: visible light, sound waves, physical contact. These senses kept our ancestors alive. They're sufficient for navigating the human scale world. But the universe doesn't care about human scales or human senses. Most of what exists is invisible to us, not because it's far away or behind something. Invisible fundamentally, not interacting with light at all. This is a profound lesson. Reality is bigger than perception. There are aspects of the universe we cannot directly sense, but which nonetheless exist, and shape everything around us. Second, it tells us that science works. We can detect things we cannot see. We can infer properties of things we cannot touch. We can develop theories about things beyond direct experience, and test those theories through observation. Dark matter was discovered not by seeing it, but by noticing its gravitational effects. Scientists measured galaxy rotation speeds, found they didn't match expectations, and deduced that something invisible must be present. Asterisk, that's the power of the scientific method. Observation, hypothesis, testing, refinement. Even when the thing you're studying is invisible, even when it barely interacts with ordinary matter, you can still figure it out through careful reasoning and precise measurement. Asterisk third, it tells us that the universe is stranger than we imagined. When I was young, I thought the universe was made of stuff like Earth rocks, gas, maybe exotic states of matter like neutron star cores, but fundamentally variations on familiar themes. Asterisk dark matter is different. It's not just exotic ordinary matter. It's something entirely new. A type of particle not in the standard model, interacting only through gravity, making up most of the matter in the universe. Asterisk, that's genuinely weird. Reality is weirder than our theories predicted. Nature surprised us. Asterisk, and this has happened before. Quantum mechanics was weird. Relativity was weird. Black holes were weird. Dark energy is weird. Each time, nature turned out to be stranger than we expected. Asterisk, what does this tell us? That we should expect more surprises. That reality doesn't conform to human intuitions. That the universe is under no obligation to be easily comprehensible. Asterisk fourth, it tells us that we're made of rare stuff. You, me, Earth, the sun, we're all made of ordinary matter. The 5%, the minority component. Asterisk, most matter in the universe is dark matter, which never forms stars or planets or life. Dark matter just flows through space, creating gravity wells, shaping structure, but never organizing into complex structures like solar systems or biological organisms. Asterisk, we're unusual. We're made of the stuff that can form atoms and molecules and chemistry and life. The stuff that interacts electromagnetically, allowing complexity to emerge. Asterisk, in a sense, we're rarities. Not because Earth is special cosmically, it's just one planet among billions of trillions, but because we're made of the unusual type of matter. The kind that does more than just provide gravity. Asterisk finally, it tells us that we're still in the early stages of understanding the universe. We've made enormous progress over the past few centuries, from thinking Earth was the center of everything, to understanding we're on a planet orbiting an ordinary star in an ordinary galaxy, in a vast universe. Asterisk, but we're not done. We don't understand dark matter. We don't understand dark energy. We don't fully understand how galaxies form, how the first stars appeared, what happens at black hole singularities, whether the universe is infinite. Asterisk, there's so much left to discover, so many questions unanswered, and that's exciting. Asterisk, we're now living at the end of science, when everything is known. We're living during an active period of discovery, when fundamental mysteries remain, when new observations regularly surprise us, where the universe keeps revealing aspects we never suspected. Asterisk, dark matter is one of those mysteries, a reminder that despite all we've learned, nature still has secrets. Asterisk # the human element. Asterisk, let me tell you about some of the people behind the dark matter story. Because science isn't just about equations and observations, it's about people, persistence, and the willingness to question what everyone knows. Asterisk, Fritz Zwicky, who first proposed dark matter in the 1930s, was brilliant but difficult. He insulted colleagues, called people spherical bastards because they were bastards no matter which way you looked at them. It was generally unpleasant. Many scientists dismissed his ideas partly because they didn't want to engage with him. Asterisk, but he was right. His measurements were correct. His logic was sound. And it took decades for the scientific community to recognize this. Because sometimes personality gets in the way of truth. Asterisk, Vera Rubin, who provided definitive evidence for dark matter through galaxy rotation curves in the 1970s, faced gender discrimination throughout her career. She was denied access to the Palomar Observatory because she was a woman. She had to fight for telescope time, for recognition, for respect. Asterisk, but she persisted. She made meticulous observations. She gathered undeniable evidence. And eventually, the scientific community had to accept her conclusions because the data was too good to ignore. Asterisk, Rubin died in 2016 without winning the Nobel Prize, despite her fundamental contributions to our understanding of the universe. Many think this was an injustice, though the Nobel Prize has its own complex politics and limitations. Asterisk, the point is, science is done by humans. Flawed humans with biases and blind spots and personal conflicts. But the scientific method, when followed rigorously, eventually converges on truth regardless of personalities or politics. Fritz Zwicky was right even though people didn't like him. Rubin was right even though she faced discrimination. The universe doesn't care about human social dynamics. Evidence wins eventually. Today, thousands of scientists are working on dark matter. Experimentalists building detectors, theorists developing models, astronomers making observations, graduate students analyzing data, technicians maintaining equipment. They're motivated by curiosity, by the desire to understand, by the thrill of potentially making a discovery that would rewrite textbooks. Some will spend entire careers searching for dark matter particles and never find them. That's the reality of this kind of science. You might spend 30 years building increasingly sensitive detectors, searching for a signal that never comes, but every no result teaches us something. Every experiment that doesn't find dark matter narrows the possibilities, constrains what dark matter can be, pushes us toward the truth. Science is often slow. It's often frustrating, but it works. And the people doing it, despite all their human flaws, are engaged in one of humanity's greatest endeavors, trying to understand the universe. What happens next? So where does the dark matter story go from here? What should you expect in the coming years and decades? Experiments will get more sensitive. The next generation of direct detection experiments is already being planned and built. Larger detectors, better shielding, lower backgrounds. If dark matter particles interact with ordinary matter at all, we're getting close to the sensitivity needed to detect them. New telescope observations will refine our understanding. The James Webb Space Telescope, the Vera Rubin Observatory, and future missions will observe galaxies with unprecedented detail. We'll better understand how dark matter is distributed, how it affects galaxy formation, how it evolved over cosmic time. Particle accelerators will probe higher energies. Future colliders might create dark matter particles in the lab. Even if they don't, they'll test theories that predict dark matter, helping us narrow down possibilities. Computer simulations will become more sophisticated. As computing power grows, we'll simulate the universe with greater resolution, including more physics, matching observations more precisely. This will help us understand dark matter's role in structure formation and galaxy evolution. We might detect a signal. This is the big one. At some point, maybe next year, maybe in 20 years, an experiment might detect something. A particle interaction in a detector, an unexpected gamma ray signal, a reproducible anomaly that demands explanation. If that happens, everything changes. We'll finally know what dark matter is. We'll be able to study its properties. We'll understand what 85% of the universe's matter is actually made of. Or we might not detect anything. We might rule out every candidate particle. WIMPs might not exist. Axions might not exist. Sterile neutrinos might not exist. That would also be important. It would tell us dark matter is even stranger than we thought. It would force us to consider possibilities we've overlooked. Maybe dark matter interacts so weakly we'll never detect it in labs. Maybe it's a modification of gravity after all. Maybe it's something we haven't imagined. Either way, detection or continue no results, will learn something. That's how science works. You ask nature a question through experiments and observations. Nature answers. Sometimes the answer is surprising. Sometimes it's not that, but it's always informative. Living with mystery. I want to address something important. It's okay not to know. It's okay to have unanswered questions. It's okay to live with mystery. Some people find it uncomfortable that 95% of the universe is unknown. They want answers now. They want certainty, but that's not how the universe works. Reality doesn't owe us easy answers. Nature is complex, subtle, often counterintuitive. Understanding takes time. Think about how long it took to understand gravity. Newton described it in the 1600s. Einstein provided a better description in 1915. We're still learning about it today through gravitational wave observations. 3 centuries of progress, and we're still discovering new things. Dark matter has been known for only about 90 years. We've made enormous progress. We know it exists. We know its distribution. We know roughly how much there is, but we don't know what it is yet. That's okay. That's normal. That's how science works. Asterisk, some mysteries take generations to solve. The nature of light took centuries. The structure of atoms took decades. The origin of the universe is still being refined. Asterisk, dark matter will eventually be understood. Maybe not in our lifetimes. Maybe the key discovery happens after we're gone. But eventually, through persistent observation and experiment, we'll figure it out. Asterisk, in the meantime, we live with the mystery. We acknowledge what we don't know. We keep searching, keep experimenting, keep thinking. Asterisk, that's not a weakness. That's honesty. That's intellectual humility. Asterisk, and there's something beautiful about it. We live in a universe still capable of surprising us, still full of mysteries, still offering new discoveries to future generations. Asterisk, how boring would it be if we understood everything? If there were no mysteries left? If science was complete? Asterisk, dark matter reminds us we're not there yet. The universe still has secrets, and that makes it exciting. Asterisk, hash the invisible universe. Asterisk, let me bring us to the end with a final thought. Asterisk, right now, at this moment, you're surrounded by dark matter. Billions of particles passing through you every second. Invisible, intangible, undetectable by any human sense. Asterisk, those particles have been here since the Big Bang. They've been flowing through the solar system for 4.6 billion years. Through Earth since it formed. Through every living thing that's ever existed. Asterisk, they're ancient. They're everywhere. And they're invisible. Asterisk, the universe you see, stars, galaxies, planets, is just a minority component. The glowing parts, the bits that interact with light. Beautiful and wondrous, yes, but representing only 5% of what exists. Asterisk, the majority is invisible. Dark matter providing the gravitational framework. Dark energy driving cosmic acceleration. Together making up 95% of the universe. Asterisk, you live in an invisible universe. Most of what exists is beyond your direct perception. You see the lights, but the scaffolding holding it all together is hidden. Asterisk, that should change how you think about reality. What you see isn't all there is. Perception is limited. The universe extends far beyond what eyes can detect or hands can touch. Asterisk, but that doesn't mean it's unknowable. Through science, through careful observation, through logical reasoning, we can map the invisible. We can infer what we cannot see. We can understand what we cannot touch. Asterisk, dark matter exists. We know this. We've mapped it. We understand its distribution. We know it holds galaxies together, shapes cosmic structure, makes the universe possible in its current form. Asterisk, we don't know what it is yet. That mystery remains. But we're searching. We're getting closer. And one day, maybe soon, maybe decades from now, we'll figure it out. Asterisk, until then, we live with the knowledge that most of the universe is invisible. That reality extends far beyond perception. That the cosmos is stranger and more mysterious than most people imagine. Asterisk, dark matter is out there. Around you, through you, holding the universe together. Asterisk, invisible, yes, but real. As real as anything you can see or touch. Asterisk, and that's the universe you live in. Mostly invisible, mostly mysterious, mostly unknown. Asterisk, but knowable, eventually. Through persistence and curiosity and the scientific method. Asterisk, that's the story of dark matter. The invisible thing holding the universe together. The mystery that reminds us how much we have yet to learn. Asterisk, if you've made it this far, thank you for joining me on this journey through the invisible universe. If you found this exploration valuable, a like or subscribe would really help the channel continue making content like this. These deep dives into cosmic mysteries take enormous effort to research and create, and your support makes it possible. Asterisk, and remember, right now, as you're reading this, billions of dark matter particles are passing through you. They've been doing this your entire life. You've never felt them. You never will. But they're there, silent witnesses to your existence, ancient travelers from the Big Bang, holding the universe together in ways we're only beginning to understand. Asterisk, sleep well tonight. And when you look up at the stars, remember, what you see is just the beginning. Most of the universe is invisible. Most of reality is hidden. And that invisible scaffolding, that dark matter, is what makes everything else possible. Asterisk, the universe is held together by something we cannot see. Asterisk, that's both humbling and wonderful. Asterisk, good night. And may you never forget that reality extends far beyond what your eyes can show you.